I put the sample test is posted, so it's on the Blackboard page, right, in the usual spot where the sample tests are. So so that's ready to look at. Remember, we have our last test. It's 2 weeks from today now, okay, on the whatever that day is, the 25th, I think. So so that's ready for you to start practicing. But we're still going to have homeworks, of course, up until that test, right? So this homework was actually due. This homework in this quiz was actually due Saturday, but so about half the class maybe worked on that, okay, and then I had half of you guys not working on it. So so I know Saturday deadlines are a little bit awkward sometimes, so I reopened these until today, okay, so if you haven't worked on these, then here's your chance to finish those, without losing any points. Of course, you can work past the deadline, but you're going to lose that penalty, right, if you do that. So, look, we're going to be keeping up a pretty steady pace of homework, right, okay? Plus, you've got the review to work on, so you're just going to have to be consistent, right, and apply yourself and, work on the homeworks, on a fairly regular schedule, if not every day, okay, so you can finish these things by the due date, but especially by the test. So I posted a couple of other homeworks here, 4.1 and 4.2. These there are not many problems in each one of them, and a lot of the problems don't involve a lot of calculations, so these will go pretty fast. I think combined there may be 20 problems, so and some of the problems are just problems where you can answer pretty easily, without doing a lot of calculations, as I mentioned. So anyway, these are due together on the same day because they're both on the same topic, which we're going to talk about today, okay? But in the meantime, then, you've got this other homework about quadratic functions. That's homework 3.3, and that's due on Thursday, okay? So is that Thursday? Thursday. Not Wednesday, but Thursday. So, and we'll finish what we're going to discuss about this homework right now, as a matter of fact, okay? Unless y'all have some intervening questions. I'm going to launch right into it, okay? So I am going to be doing a lot of talking between now and the end of the semester because we have quite a few topics that we still have to get through by the end of the semester, so it's going to be kind of lecture heavy until then. But y'all have gotten kind of, you're, 2/3 of the way or further past your first semester, so I think your tolerance for lecture there has gotten high enough that you'll be able to at least make it for a couple of weeks, okay, with me talking a lot, all right? So just want to give you a heads up on that, but not completely because we've got still some activities that we're going to finish today, okay? So we are going to do that a little bit later on, okay? Well, I asked for questions and then I give you all a chance. Do y'all have questions that you want to ask? Yes?
So for all of our work, once the semester finishes, it will all be counted up together, and that's when it will truly go in on the record, right?
That's right. So, well, your current average, as it shows in my math lab, is sort of correct as of now. But there are lots of components there that are missing, right? So, because you still have a third test and the final exam, which is a big chunk of the grade. Okay, so that can have a strong influence on your grade, hopefully positive, but also negatively as well, right? Okay, so so you still got those two big missing pieces, which I think are over half the grade still to be determined. Okay, right. So at the end of the semester, then we'll calculate your average based on all of these things according to the percentages that are in the syllabus, right? Okay, so and then whatever your average is, that will determine the letter grade. So what goes on your what goes on your transcript is not an average. It's just it's a letter grade. Okay, so that might be a little bit different from, I don't know how grades are assigned now in high school. Okay, it may actually show an average, but in college it won't show an average. It'll just show a letter grade. So A actually encompasses a wide range of scores there, right? That would be from 90 to 100, right? Okay, that would be an A, and then B would be from 80 to 89. So that's also kind of a wide range. That's just how letter grades are assigned. Okay.
Test correction. You can still turn those in, right?
There are no test corrections.
Not for this new one.
No test corrections, right? So, yeah, right. So I think you've confused this. Well, I'm not sure what you're referring to, but maybe you're thinking of another class as doing test corrections. So we don't have test corrections here, right? Okay. Whatever grade you get on the test, that's going to be it, okay, for that particular test, right? But you do want to do your test corrections correct, because that's important for two reasons: improving your grade on the subsequent test, right? And then but of course, improving your performance on the final, because the final is comprehensive. Okay. Oh, so that reminds me now. There will be a final exam review. That's a large final exam review, so it's for all sections. It's not specific to this section, but it's a final exam review for all sections. That will be, I think it's the Monday following. I'll give you the schedule. Precisely next time, but I'll put it on the announcements. But it's going to be the Monday following Thanksgiving, so whatever day that is, okay, we can count forward, December 1st or something like that, okay. But it will be on a Monday, and it'll be in the morning, so maybe that will give you a better opportunity to, and that's a reading day, so there won't be any classes scheduled that day on Monday, December 1st, or Tuesday, December 2nd. Final exams for all classes will not start until Wednesday, December the 3rd. I forgot when our final exam is specifically, but in general, final exams start on that Wednesday, okay? And then they go for a week, so you may have final exams anytime in that week after the 3rd. But anyway, there will be a large final exam review based on a review sheet that I will provide to you, okay? So you will have a review sheet also for the final exam. Of course, the one for the 3rd test is posted, right? Now, there's one other unusual opportunity that you get, okay, here in college algebra. On December the 2nd, the day following the review, which is still a reading day, so no classes will be scheduled that day. But there may be other activities going on campus, such as on that day you'll have an opportunity to take a pre-version of the final exam online. Okay, so it's an electronic version of the final exam. And you'll take that through my math lab, okay? Just like doing your homework in my math lab, you'll sign in and you can take the final. It's proctored though, so you have to go to a particular location to take that, okay? And then, but of course, your regularly scheduled final exam will also occur. That will be on pencil and paper, all right? So you get, in effect, 2 opportunities to take the final exam, okay? And if your score is high enough on the electronic version, the one on December 2nd, then you don't have to come back and take the paper and pencil final exam if you're happy already with your grade, okay? But also, it gives you an idea of sort of previewing the final exam, right? So it's just another way of helping you prepare for the final exam. If you take it once, you realize, these are the things I know and these are the things I don't know that I'm going to need to know. It may focus your studying a little bit better for the actual paper and pencil final exam. Let's see, what was your question?
So in my math lab, most of the answers are multiple choice. Would
Right.
that be multiple choice, or would it be open-ended since our tests in class are open-ended?
Yeah, no, the final exam is multiple choice, okay? So the 3rd test will not be, though, all right, okay? All right, some of the questions in my math lab are multiple choice, right? They're not all multiple choice. But the final exam is multiple choice, but it is comprehensive, so please keep that in mind, okay? It's going to be comprehensive, so it will be the entire course, right? You'll be responsible for, okay? Right. So that's the way that's going to work. Now, look, for that E-final, which is optional. You don't have to come to take the e-final. You'll have to take either the e-final or the paper and pencil one, though, right? Which is at the regularly scheduled time. But for that e-final, you do have to sign up, okay? So it's not just something that you show up someplace. You've got to go and register to be eligible to take it. So that will start on Wednesday, I'm told, okay? On Wednesday morning in the Math Center, North 925. So on Wednesday morning in the Math Center, you can go and register for the e-final, and they'll give you the instructions for where you will report and that sort of thing, what you need to bring with you, and et cetera, correct? Okay. So Monday morning in the Math Center, North 925, that's where you sign up. Now, those things have limited seating. So if you want to do that, you need to make a decision quickly because the slots will fill up fast, all right? So if you wait too much past Wednesday, then all the seats will be taken, okay? And then you won't have that opportunity to do that e-final, all right? Okay? So because it's first come, first served. So when it's filled up, it's filled up, okay? Be thinking about that. But if you're, if you're just thinking, oh, I'll just sign up and then I'm not going to show up, don't do that. If you sign up, you need to go ahead and report because that's going to deprive someone who is serious about it possibly from taking the exam, right? Okay, the online version. All right. So don't just try to reserve a spot and then not show up. Okay. If you want to take it, fine. If you don't want to take it, that's fine. Also, it's optional. Okay. All right. So there's some of things that are upcoming here as we move toward the end of the semester. I'm going to go back now and finish talking about complex numbers and their applications to quadratic functions, and then we'll be through with quadratic functions. And then we're going to look at functions that are actually just generalizations of quadratic functions called polynomial functions. Let's see if I can get my note switch there. Okay, so remember, before last week we were talking about this huge set of numbers called complex numbers, right? And complex numbers have this form, a plus bi, where a is a real number. This sign can be negative, but it's a real number combined with, remember, an imaginary number. And the imaginary numbers were developed, recall, to allow us to extract square roots of negative quantities, okay? So the basic imaginary number is I, right? And that's defined to be the square root of minus 1. But you can develop square roots of other negative values, right, by taking just a coefficient times the I, okay? And whenever you have a coefficient here times the I, that's called an imaginary number. But when you combine, through addition or subtraction, when you combine a real number with an imaginary number, that combination gives you what's called a complex number, okay? And that big set of numbers includes both the pure imaginary numbers, like square root of minus 1, but it also includes the real numbers as well, okay? So real numbers also count as complex numbers. But complex numbers include a lot of numbers that are not just purely real numbers or purely imaginary numbers. Since complex numbers are numbers, right, we talked and saw a few examples last time of how you can do arithmetic with complex numbers. And that's pretty easy to do. The thing that you really need to keep in mind when you're doing arithmetic with complex numbers is that, remember, when you take the imaginary number I, right, square root of minus 1, and square that, that's going to give you negative 1, okay? So when you're doing arithmetic with complex numbers and you end up with the quantity I squared, you must recall that that simplifies to minus 1, okay? And with that, actually, that armed with that piece of knowledge, arithmetic with complex numbers really becomes pretty straightforward, okay? Not too bad. Not really much more difficult than arithmetic with real numbers, and of course you've been doing arithmetic with real numbers for a long time, right? Okay, but what I really want to show you here is the relationship between complex numbers and quadratic functions and quadratic equations, because that's what we're really studying in this chapter. And so let's look at a quadratic equation, and let's see how complex numbers are going to help us with this quadratic equation, which of course we want to solve, right? Okay, so our instruction here is just solve this equation, which we know is a quadratic equation, right? Because we have the x squared, correct? So we have a couple of basic techniques, right, for solving quadratic equations. One of which is factoring, if that's going to work, right? Okay, so that's useful. And then the second technique, remember, is the quadratic formula. Okay, factoring only works sometimes, right? Okay, if you can get an expression to factor, factoring will work. But the quadratic equation always applies. Okay, so you can always use the quadratic formula always applies. So you can always use the quadratic formula to help you solve quadratic equations. All right, so, well, let's try solving this one then. Before you either try factoring or, however, using the quadratic formula, make sure that you set the equation to 0. So this is important for quadratic equations. You don't necessarily do that for, say, linear equations, where you don't have the unknown squared. You may not set the equation to 0, but for quadratic equations, usually you're going to want to set the equation to 0. Okay, so I'm going to do that here. And that's easy to do, right? I'm just going to subtract 5x from both sides of the equation. So I'm going to shift that positive 5x that's on the right-hand side. I'm going to shift that back to the left. So I have 1/2 x squared minus 5x plus 17. That's equal to 0. So I've got it set equal to 0 like I wanted, right? And now we can try factoring. Or if we're not going to get anywhere with the factoring, right, then we can use the quadratic formula. All right. Well, I don't think factoring is going to work very well here because of this leading coefficient of 1/2, right? So that's going to make the factoring complicated. So let's jump right into trying to use the quadratic formula. Or something else you could do here is you could try to get rid of the 1/2. If you don't like working with fractions, you can try to get rid of the 1/2 by multiplying all the terms, right, by 2. So that would give you 2 times 1/2 x squared is x squared, and then you can multiply the minus 5x by the 2, and then you can multiply also the 17 by the 2, okay? But I think in this case, that step's not really necessary because I think we can use the quadratic formula pretty easily without worrying about that leading coefficient being 1/2 or not. Let's see, what are our coefficients here? Because we're going to need those for using the quadratic formula, right? So let's write them down. What's the a coefficient? 1/2, right? Yeah, that's just the leading coefficient. And the b coefficient there is what? What now? -5, right? Yeah, be sure you put the minus sign there. So it's -5, and then the constant coefficient is 17, right? Okay, so let's plug those into our quadratic formula. So remember the formula, let me just write it down symbolically first. It's minus b plus or minus, right, the square root of b squared minus 4ac, all of that divided by 2 times a. So I get minus a -5 plus or minus square root of -5 squared. When you plug that -5 into that expression, be sure you put it in parentheses so you're squaring the minus as well. So don't make a sign mistake there. And then -4 times a is 1/2, right? And c is 17. And then all of that over 2 times a, but that's 2 times 1/2. So that works out nicely, right, in the denominator, because 2 times 1/2 is 1. So I only have a denominator of 1 here, so really don't need to bother with that. So I have 5 plus or minus square root of -5 squared is 25, right? Positive 25. And now let's see what that second term is there under the radical. So minus 4 times 1/2 is negative 2. And then negative 2 times 17 is minus 34. And again, the denominator is 1, so I can just leave the denominator off. So I have 5 plus or minus the square root of, whoops, negative 9, right? Okay. So see, in the past, right, I would have stopped and said, well, there's no solutions to this equation because I end up with this negative quantity under the radical, okay? But what we really meant there is there's no real number solutions to this equation, okay? So the solutions to this equation are not going to be real numbers because square root of minus 9 is an imaginary number, right? Okay? And so how do we simplify that using imaginary numbers? How can we write square root of minus 9? So I really have 5 here, plus or minus what? Yeah, what? 3i, right, okay? So square root of a negative quantity, when you simplify that, that's going to involve I, okay? So we need to keep that in mind, all right? Square roots of negative quantities are going to be imaginary numbers, so they're going to involve the number I. Let me show you why. Again here, because see, minus 9, you can write that as minus 1 times positive 9, right? Normally you wouldn't do that, but in this case that's useful. So I'm going to write minus 1 times positive 9, and now I have square root of minus 1, which by definition, right, that is I, okay? And we also have square root of 9, that's easy to extract, right, that is 3. So, so you can really extract 2 square roots from under this radical, right? Square root of minus 1 is I, and square root of 9 is 3. But normally you would write I times 3 as 3i. So you have 5 plus or minus 3i, okay? So we end up with 2 solutions to this quadratic equation after all, but they're complex numbers, right? They're not real numbers. We get, one of them is 5 plus 3i, and then the second one is 5 minus 3i, okay? So what those complex numbers have allowed us to do, well, the imaginary numbers actually, right, okay, have allowed us now to write down solutions for quadratic equations, where before we weren't able to express solutions, okay? But it turns out that in practice, it's really, in many disciplines, it's really important that you be able to write down these solutions. So you don't want to stop and say, oh, no solutions to this equation. This equation doesn't have any solutions. It turns out that these solutions in practice are useful to have, okay, rather than just saying no solutions to this equation. All right, now, look, let's check this, okay, because there's no reason to believe that, you know, everything I've written down here is perfectly correct, right? So what we think is we have 2 solutions to this equation, but let's check to see if they really are solutions. So when you've got a solution to an equation, how do you verify that that quantity you've got really is a solution? So how do you check your work? What? You plug it back in, right, okay? You have to take your proposed solution, right, and plug it back into the original equation and make sure that it verifies that equation, all right? So that's what we're going to do here, okay? We're going to take that, we don't have to, we could do both of them, but let's try one, okay? So I'm going to take here the 5 plus 3i and plug that back into the original equation and simplify and see if the equation holds true, okay? Wow, I wonder if that really is the case. So Let's see if I can remember that equation. Let me copy that. Somewhere down here. So there was the equation, right? And remember, my solutions there, one of them was 5 plus 3i, right? And the second one was supposed to be 5 minus 3i. But let's check this one by substitution into the equation. So we have to do this substitution now kind of carefully, all right? So I have 1/2 times x squared, but I'm going to plug in for x 5 plus 3i, right? So I'll have 1/2 times 5 plus 3i squared, and then plus 17, and that's supposed to come out to be 5 times 5 plus 3i, all right? So now we have to do some arithmetic here to simplify both sides of that equation, and hopefully both sides will turn out to be equal, okay? But if they don't, that means I really didn't have the solution to the equation that I thought I did, right? So here we have a little bit of arithmetic with complex numbers, but we talked about that last time, right? That's not all that hard to simplify, okay? Just keep in mind, however, that I squared, by definition, right, I squared is going to be minus 1, okay? So let's see, 5 times 5 plus 3i, that's easy to simplify. That's just going to be 25 plus 15i, okay? So that's not hard. It's the left-hand side, right, that's going to be a little bit tough. So I have to square 5 plus 3i. So remember, that means multiply it by itself, and then, of course, I have to multiply by 1/2 and then add in the 17, okay? All right, so let's dive right into this. 5 plus 3i times 5 plus 3i. So what is that? Well, this is kind of like multiplying binomials with x's in them together, all right? You just multiply every term in the first parentheses by every term in the second. So you get 5 times 5, that's easy enough, that's 25, right? And then 5 times 3i, so that's 15i, right? And then 3i times 5, that's another 15i. And then here's the part you have to be careful of. 3i times 3i, that's 9i squared, right? So I have 25 plus 30i, right? But now, what's the 9i squared? Negative 9, right, okay, because I squared is minus 1, right, okay? So remember, I squared is minus 1, and then minus 1 times the positive 9 is going to give you negative 9. So I end up here with 1/2 times 25 minus 9 is 16, right? So I have 1/2 times 16 plus 30i plus 17 is supposed to be 25 plus 15i, looking like it is, right? 1/2 times 16 is 8. 1/2 times 30i is 15i, and then plus 17, and that checks, right? 8, because 8 plus 17 is 25. Yay! All right. So see, that complex number really is a solution to that quadratic equation. Okay, because when we substitute, we get a true equation. Okay. So I think this one's going to work just as well. All right. So 2 complex number solutions to that quadratic equation. Let's try another one here quickly. So I think finding the solutions to quadratic equation is really pretty easy, right? Checking them, that's kind of, if you're going to insist on checking them, that's the part that actually can get a little bit complicated. All right, so this is definitely a quadratic equation, right? Because the unknown is squared. Okay, so we know what our strategies are, right? We might try factoring, or we might try using the quadratic formula. This is already set equal to 0, right? So you want to take your quadratic equation and you want to set it to 0. This one's already set equal to 0. So we don't have to do that part. If you try factoring here, you're not going to make it too far, right? Because the only way you could possibly factor this is x plus 1 times x plus 5. That's the only way that would possibly work. And that's not going to give you the correct middle term, right? Because you would end up with 1x plus 5x is 6x, which is a long way from 3x, right? So, so factoring is not helpful. So we can skip that. And that means we can jump right to using the quadratic formula, right, if we can identify the coefficients correctly. So what is the leading coefficient there? 1, right, yes, okay. So leading coefficient is just 1. The middle coefficient, b, is what? 3, right? And then the constant coefficient, c, obviously there are 5. So we have really nice easy coefficients here, right, for this quadratic equation. So let's see, my solutions are going to be minus b, so that's minus 3, plus or minus the square root of 3 squared minus 4 times 1 times 5, right? 4 times a times c, all of that divided by 2 times 1. So this arithmetic doesn't look too bad. Let's see. Minus 3 plus or minus square root of 3 squared is 9, right? Minus 4 times 1 is negative 4, times positive 5 is negative 20. All that divided by 2. And now we see we're going to have complex number solutions, right? Because I end up with that minus 11 under the radical. So how do we simplify square root of minus 11? 11's not a perfect square, so you're not going to be able to simplify this completely. So it's not going to be quite as nice as minus 9i, but how do we simplify that?
You would have to break it down into 2 multiple.
So I'm going to break it down as a product, Montel. What product there? Because of the minus sign, one of them is going to be minus 1, okay? And you cannot write 11 as a product, all right? Because that's a prime number. So the only way you can write that as a product is 1 times itself. So that's not really helpful here. So you're just going to have to keep the 11 there. But this is still important because what is the square root of minus 1? Yeah, square root of minus 1? Yeah, so we've just been talking about this for like 2 or 3 days, right? Okay, so square root of minus 1. That's a really important lesson. How does that simplify? How did we do it in the previous example? Let's scroll back up. So how did we do it here? There we also had a square root of minus 1, right? Okay. So what did we write down for square root of minus 1? I, right, okay, yeah. So that you have to memorize, all right? So square root of minus 1 is going to be I. That's really important, okay? That's really the whole fact that drives these imaginary and complex numbers. Now, in this example, we could also extract square root of 9 because 9 is also a perfect square. But 11 is not a perfect square. So the 11 is going to say under the 11 is going to say under the radical. So we end up here with minus 3 plus or minus. So square root of minus 1 is I, and then the 11 has to stay under the radical there. So you have minus 3 plus or minus I times the square root of 11 divided by 2. Okay? And by hand, that's really about as far as you can simplify this. Okay? So I've got 2 solutions here still, minus 3 plus the square root of 11 divided by 2, and the second one is minus 3 minus, I here, I times the square root of 11 divided by 2, okay? So, again, two solutions, but they're complex, numbers. What does that tell you, by the way, about this quadratic function? So if you were to look at f of x is x squared plus 3x plus 5, right? Okay. So just take this left-hand side of this equation and use it as a formula for a function. So what do you know about this quadratic function? Of course, when you graph it, you're going to get a parabola because it's a quadratic function, and graphs of quadratic functions are always parabolas. But what do you know about this parabola? What does this fact tell you about this parabola when you graph it? It doesn't tell you a lot, but it does tell you one important thing. Well, 5 is going to be the y-intercept, okay? But that's not what these solutions tell you. You can see that from the formula, right? That 5 is going to be the y-intercept. But what the fact that these two solutions to this quadratic equation turned out to be complex, what does that tell you about this quadratic function? Well, how would you find the x-intercepts of this quadratic function? How do you find the x-intercepts of any function? You set the formula to 0, right? So you set your function formula to 0. So if you take this function formula and set it to 0, you're going to get this equation, right? Okay. And then you solve this equation, and what did you get as solutions to this equation? What sort of numbers? What? Complex, right, okay. You did not get real numbers. So, Amber, what about x-intercepts there? See, we were looking for x-intercepts, right? So we set that to 0, right, because that's how you always find x-intercepts. And then we solved that equation. We ended up with two complex numbers. So what do we know about our x-intercepts? The solutions to that equation are complex numbers, right? Okay. So what about the x-intercepts? The x-intercepts is where it crosses the x-axis. But the x-axis consists of what type of numbers? Real numbers, right? Okay. Yeah, the x-axis is a real number line. It only has real numbers on it. But these numbers are not real numbers. They're not on the real number line. So let me go back to my original question. What do we know about the x-intercepts of that quadratic function? What? No, they cannot be real numbers, right? Because we just solved this equation. You just told me they weren't real numbers. They're complex numbers, right? Okay. So, again, what do I know about the x-intercepts there? Well, they don't. They don't fall on the real number line. But what does that tell you, Kevin? I mean, I said that. You tell me something different. What does that tell you about the x-intercepts? Shall we? Okay, y'all are going to force me into the obvious here. All right. What doesn't touch the x-axis? The graph doesn't touch the x-axis, right? The graph cannot touch the x-axis, right? It doesn't have any x-intercepts. The graph does not have x-intercepts, okay? Because if it had x-intercepts, these could not come out to be complex numbers. These would be numbers on the x-axis, right? But the x-axis consists of real numbers. So you know you don't have, this curve does not cross the x-axis, all right? That curve doesn't cross the x-axis. Actually, you could see that, you could discover that in other ways, okay? Another way you could discover that is figuring out where's the vertex. Let's figure that out, Where is the vertex? So remember our formula for the vertex? Because you're going to have to know it for the test, okay? Both the test number 3 and the final exam, all right? You're going to have to know the vertex, okay? You're also going to have to be able to answer trivial questions like this one, all right? So I'm really alarmed about what's going to happen on test number 3, okay? Y'all are going to be, hey, the thought of y'all repeating this course next semester, okay? Because you're going to have to buy the book again, all right? Oh, yes. And you're going to have to pay tuition. Well, not if you bought a multi-semester. Did you buy multi-semester? Oh, okay. All right. Well, this is my warning to you guys. If you are taking the class again, right, okay, you have to buy the book again. Of course, you have to pay tuition again. What a phenomenal waste of money. All right. So, where's the vertex here? You don't pass the class automatically, Montel. Right? Okay. The grade you get is the grade that will go into the onto your transcript. I don't curve grades, so whatever that shows at the end of the semester, that's what's going down. All right. How do you find the vertex? What's the formula? Yeah, minus b over 2a. So what's that going to be in this situation? Let's see. We had the a, b, and c written down here, right? The b is 3, right? So we have minus 3 over, and the a is easy. That's just 2 times 1, correct? So the x-coordinate of the vertex is minus 3 halves. Somewhere about right there is minus 3 halves. And then how do you find the y-coordinate of the vertex? This is the x-coordinate. So how do you find the y-coordinate? What do you do with that minus 3 halves? Yeah, you plug it into the function. Sure, right, okay? You have to calculate it. So we're going to compute here f of minus 3 halves, all right? All right, so that's a little bit of arithmetic, but not terrible, okay? We get minus 3 halves squared plus 3 times a minus 3 halves, right? Okay? And then don't forget the 5 that's added on, because I think that's going to be important. So let's see. Minus 3 halves squared is 9/4. And then minus 9 halves, because 3 times a minus 3 halves is minus 9 halves plus 5. So you get 9/4 minus 9 halves. That turns out to be negative 9/4, okay, plus 5. So how many fourths do we end up with here altogether? Minus 9/4 plus 5? I think that's 11/4. Because 5 is 20/4. So you get minus 3 halves as the x-coordinate and then 11/4 as the y-coordinate. So 11/4 up here, a little bit more than 2. Right there is your vertex, right? And which way does that parabola open? Up. Right, okay. So it opens up. Probably not making a very accurate graph here because it's got to cross the y-axis at 5. So I didn't draw that very carefully. But it does open up, right? Okay? Which means the same thing that we had already discovered, right? It's not going to cross the x-axis. It doesn't have any x-intercepts. Because when we try to find the x-intercepts, they turn out to be complex numbers, right? Okay? Not part of the real number line, not on the x-axis, because the only thing on the x-axis are real numbers. Okay, all right. So we've got an activity about this, right, on our activity sheet 6. Okay, so did y'all bring 6 back with you? Because we still have not finished the back here of this activity. So I'd like to try that one now while this is fresh in our mind. Some of you may have already done it. Okay. So on the back of that, let me switch over to the dot cam here, right? So so this is a question very much like the examples there that we just did, okay? So there we have an equation to solve. That's obviously a quadratic equation, right? Okay, so we want to solve that one. And Then, just to make sure that we did our work properly, we want to verify one of the solutions. You don't have to verify two solutions. If you get two solutions, remember, you may get two solutions, right, to that quadratic equation. But we want to pick one of the solutions. Either one is fine, okay? And then verify that by actually substituting it into the equation, just like we showed in the example, right? Okay. So we're gonna find the two solutions and then pick one of them, your choice, and substitute that in to the equation for the variable x and simplify and see if it works. Okay. See if you really did find a solution to that equation. Let me switch back to the notes for a second. I'll scroll up there to where we were verifying, or down, I should say. Remember, here's where we were verifying one of the solutions to this equation. So when you find one of the solutions to that quadratic equation on the worksheet, you can sort of use that as a guide, right, of how we substituted and checked it there. Okay. All right, so we can go pretty quickly here. We want to find the solutions quickly. That's probably the quadratic formula, unless you can factor, okay? And then the trickier part is substituting in, right, and simplifying, okay? Until you've done that once or twice, then that's a little bit tough. Yeah. Yeah. How to get rid of the 2. Let's see. Yeah, you did not square this though, right?
Oh.
Yeah, so maybe that will make things easier. Okay. If you solve correctly, you should end up with no radicals in your solution. The square roots will completely simplify. Yeah, so what's square root of minus 4?
2? 2i?
2i, right. So first you have 4 plus or minus 2i over 2, right? So you didn't write that down yet, so write that down here. 4 plus or minus 2i over 2. Write that down, right? Okay. So you're skipping a step there. 2i. No, the square root's gone. Mm-hmm. Yeah. and then all of that over 2. Now you can get rid of the 2's easily, because 2 divides into both of those things in the numerator, right?
Here and here.
Yeah, so what would you get?
I.
Yeah, there you go, right. So there are your 2 answers. Now, one of those you got to pick and check it, either one.
Okay.
Yeah.
So
So, yeah, so Ben, how does that reduce then? 2 divides into both of those things, right?
Plus or minus I.
Yeah, right, yeah.
use the substitution of
Yeah, so one of them is 2 plus I and the other one's 2 minus I. So pick one of those and then try that in the equation. Substitute it into the equation. All right, so what's square root of 4 though?
2.
2. So you can extract that, right? You don't need to write that.
So this counts as alright?
Well, let's see. So first let's write it as equal 4 plus or minus I times 2, or 2I, right? Yeah. Now you can divide 2 into both of those things in the top, so that's nice. So we can divide out the 2. There you go. So there are your 2 solutions. One of them is 2 plus I, and then this is the other one. Now I want you to try one of those. So pick one of them and plug it back into the original equation, for x, and simplify. Okay, and see if that is equal to, well, it's supposed to be equal to 0, right? Because it was all of this equal 0. So see if that does, in fact, equal 0. You've made an arithmetic mistake here, right? Okay. So, well, yeah, well, but to calculate, here's the mistake that you made. It's b is minus 4. So when you substitute that in here, since it's a negative value, make sure you put it in parentheses, because otherwise you're going to get a sign mistake, which is just what you did. What is minus 4 squared?
16.
Positive 16, right. So this is positive 16, and this is negative 20.
So it's negative 4.
Negative 4, right, yeah, okay.
I did what he did.
Okay, yeah. So, yeah, when you substitute a quantity in,
In the parentheses.
yeah, put it in parentheses. That makes it safer. Otherwise, your life will make that mistake.
This is where I'm at, right here.
Okay, so, but you're not quite where you're at, because you didn't draw the line there all the way across, right?
Oh, okay.
And this turned out to be minus 4, didn't it? Under the radical?
Yes.
Yeah, right, okay. So what is the square root of minus 4?
2.
Something, not just 2.
2i, right here.
2i, right. Oh, I see. So you had this.
Yeah.
Yeah, remember the fraction line goes all the way
Oh,
across.
okay.
But now that you can reduce that. This is nice, because 2 divides into both of these things.
Right.
So what would that reduce to if you divide 2 into both of those things?
2i.
2 into here and 2 into here, right? So you're going to have to write it down. So you would have what?
2 plus or minus I.
Right, 2 plus or minus I.
Okay.
2, and then all that's left here is the I, because
Right.
that 2 divides
Okay.
out. So you have 2.
So you would have 2 answers, though, right?
Yeah.
Would you write it
2
like how?
plus or minus I, right? Yeah, right.
Okay.
2 plus minus I. And so you've got 2 answers there. One of it is
Right,
2
2
plus
plus
I,
I
and the other one is 2 minus I,
Okay,
right?
got it.
Okay.
Oh,
Now,
okay.
one of those, your choice of those 2, you want to take it and substitute it into the original equation for x. And do the arithmetic with the complex numbers and see if it reduces to 0. Because if it does, then you have the solution. If it doesn't, then something is off, right? Okay. All right. Now, yeah. So, now you're plugging in. Okay, great. Yeah, that's exactly what you want to do.
Oh, I should have plugged it up here, not here. That's alright.
But the x is going to be gone.
So it's going to be 2 plus
Like squared.
Ooh,
Yeah, right. Because the x is squared, correct? Yeah, now how do you no, the x is gone. You're plugging in this number for x. So the x is gone, but this is squared. Instead of x squared, you have this squared, right? Okay. Now, can you multiply that out? Okay. Now try multiplying that out like we multiplied that one, right? That example. Did y'all get 0 yet?
No, but right, Mister, like you carry this negative 4 here and here.
Yes, so this is right, this is right, right. This is right, okay? So you have 4 plus 4i, but what's I squared? By definition, what's I squared going to simplify to?
Isn't it just I? Or
No. That's the whole point of I. When you square it, what do you get?
Wait, I squared.
I'm going to smack you
If
on the
it's
head because this is what we've been doing
if
the
it's
whole time, okay?
if it's square root of -1, right? Times square root of -1.
Is
It's
what?
just I.
No. When you multiply square root of a square root of a quantity times square root of a quantity, what does that give you?
I think I just
The quantity.
yeah.
So if I have square root of -1 times square root of -1, what's that going to give me? Ah, there you go. So what's I squared? -1, right. Yeah, you got to freeze that into your memory. I squared is -1. So you have -1 and then a 4, right? So -1, this 4 is still there, right? So you have -1 plus...
I already simplified the numbers.
Oh, okay. So, well, what's -1 plus 1?
0.
Ah, so you have 0 equals 0. That's what you want, right?
Okay.
Yay, right, okay. Yeah, that's true. 0 does equal 0, right?
Okay,
So you got what you wanted. Yeah, okay. So that those were solutions to the equation, okay?
why did I use pen?
Okay.
I need a check, sir. I feel like I went off of the trail. I was doing well, but
Okay, so what's square root of -4? Is that an I?
that's a -2.
No. What's square root of -4?
Well, nothing.
No. We just wrote this. What's square root of -9? That was in one of our previous
That would
examples.
be -1 and I.
And not -1 and I.
Or -3.
Not -3 and I. It's just 3i.
Oh.
Yeah, not a negative. I is used to take square roots of negative quantities. So what's square root of -4?
That would just be 2.
2 something I, right. So put that there. It's 2i, okay? All right, so what am I looking at here? Okay, so what's your final...
I'm still checking.
Oh, you're still checking?
Yeah.
Okay.
Checking which one it is.
All right, so so that is not a plus though, right? Is that supposed to be a plus? And isn't it a minus up here? Looks like you transcribed it as a plus. Right there, right? Okay. Because that will help, I think, if that's a minus. But what is I squared by definition? What's the whole point of I? So when we square it, yeah, we get -1, right? Okay. So wherever you see I squared, you can substitute in -1. Okay, you got it there. Except 2 divides into both these things. So 2 goes into 4, what? 2, and 2 goes into 2i, what?
1.
No, what's left? I, yeah. So write that down. You have 2. This is 2. Then the plus or minus is still there. And then this is, there you go. There are your 2 solutions. 2 plus I and 2 minus I. Okay. Now, all right, so you got the 2 solutions. Now pick one of those. You can either do 2 plus I or 2 minus I. And you want to substitute it for x in the equation. So wherever you see x in here, you want to write down one of the solutions. And then do the arithmetic and see if it's true. Okay. So let me see you do the substitution. Ah, right. Okay, so we want to check, does all of that come out to be 0? So when you simplify all of that, do you get 0? All right, so try simplifying it, see if it reduces all to 0. Did that reduce to 0 yet?
Yeah.
Yes. Right, yeah. Okay. 1 minus 1? Yeah, okay, so that's 0. Right, okay. So you have verified one of your solutions there. You need to... Okay, so let me see that. Be sure you put that in parentheses. All right, okay. So can you square that? That means you have to multiply it by itself. All right, so just write it side by side and multiply it by itself. You got 0. Y'all got 0? You got to 0 yet?
No, I'm
Okay.
still working on it.
Okay.
Yeah.
You're getting close though, except you. What did you do here? Isn't this minus 8 minus 4i? Isn't that a 4i there? Right? Because you took the minus 4 times the I. Yeah. Okay. Okay. Halfway. There are your two solutions. Now you have to verify those by substitution. So you have to take one of them, either 2 plus I or 2 minus I, your choice, and you have to plug it in for x in this equation. Yeah, into this equation and do the arithmetic and see if it reduces to 0. Is that reduced to 0 yet?
Wait, so if it's 2 i's, would it be 2 I squared?
No, if it's just I times I,
Is
is I squared. Yeah. But what is I squared? This is the whole key thing. How much is I squared?
Negative
1,
1?
right. Yeah, by definition it's minus 1. So where you see this, you can change that to minus 1.
For every I?
Not just this one.
Okay.
Yeah, just I squared. I is not minus 1, but I squared is minus 1. Yeah, okay. Did it come out yet? So how much is that? Negative 1. So where you see that, right, minus 1. Now try combining your terms together. A lot of these things will combine. The i's will combine, the constants will combine, but remember this is minus 1. So when you see that, you have to put in minus 1.
Okay.
Yeah, so you can just change that automatically to minus 1. Did you get that too? Yeah, there you go, right. Okay, so, yeah, that's...
No, Dr. Waller, I'm stuck.
Okay, so you didn't square that right. That means you have to multiply it by itself. It's not this, right? You have to take it and multiply it by itself. So write it by itself, side by side. Yeah, right. This by itself, right? That's what it means to square something. Is multiply it by itself, correct?
So 2 plus...
You would write, yeah, 2 plus I times 2 plus I, because that's 2 plus I squared, right?
Right.
Now multiply that out. Yeah,
And then
multiply
when you
that
get
out.
to this part, is it negative 4 times 2 and then negative 4 times I?
Yes, yeah. Multiply both of those. Did y'all get it? Did y'all reduce it? Okay, let's see where you went off here. This looks all correct, but you went crazy right here. How much is I squared? This is the key point. Negative 1. So you put in there a minus 1. Yeah, and then what did you do here? This is just 4i, not 4i squared. That's just 4i. You're not multiplying those. You're just adding them. Yeah, 2i plus 2i is 4i. So that shouldn't be there. Now I bet everything will cancel.
Yes.
Does everything cancel? Yeah, and you should come out with 0 equal 0. So what did you do here? This is right up to here. Did you put the minus 1 in there? So minus 1, yeah, this is 4 plus 4i. Did all those things cancel each other? I think they will. But have they canceled each other yet? Yeah, they did. This is 4i minus 4i, that's 0. And this is minus 9 plus 9, that's 0. Yeah, so you get 0 equals 0, which is correct, right? Okay, 0 does equal 0.
When you're doing this, you separate here.
Yeah, no, you're not, because what is I squared? By definition, what's I squared? This is the whole key, negative 1. So you have 4 plus 4i minus 1. How does that distribute now? What's minus 4 times 2 plus I?
Negative 8.
Negative 8. And then minus 4 times I is
Negative 4i.
negative 4i, and then plus 5. There you go. Does all that add up to be 0? I think it does. Check it. See if all that adds up to 0. Good. Yeah, I got a little bit of complex arithmetic under your belt. You have to remember that I squared is minus 1, right? Okay? That's the key to doing this complex number arithmetic, is just that simple fact. So the solutions here, without going through that, turned out to be 2 plus I and 2 minus I. So I think everyone got those two as the complex number solutions to that equation. So to check one, let me do one different. Most of y'all chose 2 plus I. Let me do 2 minus I. Check that one. So you're going to substitute 2 minus I for x in the equation. So we would have 2 minus I squared, because this is x squared, right? Minus 4 times 2 minus I, and then plus 5. And that's supposed to turn out to be 0. That's what we were trying to figure out. So we have to square the 2 minus I, multiply it by itself. Of course, this is pretty easy to simplify. Minus 4 times 2 is minus 8. Minus 4 times minus I is plus 4I, plus 5. And then let's square this. So 2 times 2 is 4, right? 2 times a minus I is a minus 2I. Minus I times 2 is another minus 2I. And then here we have minus I times minus I, so that would be plus. Minus times minus is plus, but still I squared. So see, the I square is popping up there, right? And that you have to simplify. But that is negative 1. Minus 2I times minus 2I is minus 4I. I squared is minus 1. So you replace that I squared by minus 1. Now, do all these terms add up to 0? Let's see. I have a minus 4I and a plus 4I, so those cancel, right? And let's see, what about the numbers here? 4 minus 1 is 3 minus 8 is negative 5, plus 5 is 0. So, yay, it checks, right? Okay, so the solution 2 minus I checked. I think most of y'all checked 2 plus I, and that also checked, right? So, our solutions are correct to that equation. Okay. Okay. All right, I'm going to talk a little bit more at you here now, but this is going to be pretty straightforward because except there's a lot of terminology. What we're going to do is look at situations like quadratic functions, except we're going to allow the exponent, which remember the exponent for quadratic functions was 2, right? But we're going to allow that exponent to be larger, okay? So in these functions, you might have x cubed, or you might have x to the 4th, or x to the 5th. In fact, you can have x to an arbitrarily large power, okay? So these functions we're going to refer to as polynomial functions. So they have a long name, polynomial. But these are like quadratic functions, except that your power of x may be higher, all right? So you're not limited to just having x to the first power or x to the second power. So this looks kind of abstract when you first glance at this. This is just in general what polynomial functions look like. But all this is saying is, in polynomial functions, you just have powers of x. So for a quadratic function, you would have, x squared, x, and then a constant. But in polynomial functions in general, you can have higher powers of x added in. All right? So quadratic functions are examples of, these familiar quadratic functions are examples of polynomial functions. This highest power of x, that is called the degree of the polynomial function. So quadratic functions have degree 2. okay? Because in quadratic functions, the highest power of x is 2. But in general, in quadratic functions, you may have much higher degrees. So you can have degree 3, or degree 4, or degree 5, or arbitrarily high degree for polynomial functions in general. This coefficient that's multiplied by the highest power of x, just like in quadratic functions, that's called the leading coefficient. So whatever number is multiplied by the highest power of x, that's referred to as the leading coefficient. We label that, in quadratic functions, we just simply call that a, right? But in general, in polynomial functions, since we may have lots and lots of terms here, and we may run out of letters of the alphabet, we're going to label these coefficients with subscripts. So for the leading coefficient, you're going to label that with usually a, and then the subscript will be whatever the degree or whatever the power of x is. That's just a notational mechanism so that we can give names to these coefficients in these polynomial functions, or give variable names to these coefficients in these polynomial functions. Of course, the constant that's added on at the end, that is called the constant coefficient, just like it is for quadratic functions. This, by the way, can also have a label with the subscript on it, so you can label the constant coefficient as a sub 0, okay? This b coefficient, you can label that as a sub 1, because notice that you take a and then you use as a subscript whatever the power of x is. So this coefficient, you could label that one as a sub 2, and so forth. So I'm going to tell you some things about so-called polynomial functions. We're going to look at some examples, all right? But because it's hard to look at that abstract definition of polynomial functions and understand it very well until you look at some specific examples. But I'm going to tell you some facts about polynomial functions that are kind of very similar to quadratic functions, actually, because quadratic functions are a type of polynomial function. First, of course, whatever the constant coefficient is at the end of the formula, whatever the constant is at the end of the formula, that's the same as the y-intercept. All right, so that's true for quadratic functions, right? The domain is going to be all real numbers. So domain will be all real numbers, unless there's some sort of restriction on the domain. In general, the domain will be all real numbers. And when you graph a polynomial function, you always get a nice, smooth, unbroken curve, okay? So it's unbroken and it's smooth, okay? It may have lots of turning points, though, all right? So it may be increasing and decreasing and change from increasing to decreasing or vice versa several times, okay? But the curve is going to be smooth, and it won't have any breaks in it. But you can have lots of waves in the curve. And here's really the really key facts about polynomial functions that make them really useful. For a polynomial function, you can have at most this many x-intercepts. This is the degree of the polynomial function. So whatever the degree is, that's the maximum number of x-intercepts you can have. Of course, you can only have one y-intercept, right? All functions can only have one y-intercept. But functions can have lots of x-intercepts. But for polynomial functions, the maximum number of x-intercepts is whatever the degree is. That doesn't mean that is the actual number, but that's the maximum number of x-intercepts you can have. And the number of turning points you can have, that's where it switches from increasing to decreasing or vice versa, that is always the degree minus 1. So whatever the degree is, if you subtract 1 from that, that's the maximum number of these turning points where the function switches from increasing to decreasing or decreasing to increasing. Sort of these peak points or valley points, the maximum number of those is the degree minus 1. let's take a look at some examples of polynomial functions. But you're already familiar with polynomial functions because quadratic functions are a type of polynomial function. So is a linear function. So this is a linear function, right? Of course. What's the slope here? 2 over 3, right. So it has slope 2/3. The y-intercept, of course, is -2, right? Here's a graph of that linear function over there on the right. Linear functions like this one, they count as polynomial functions, okay? So linear functions are a simple type of polynomial function. What's the degree here? So for this function, as a polynomial function, what's its degree? We always label that by n. So degree means the highest power of x. Highest power of x. So what's the highest power of x in this function? 1, right, okay? So this has degree 1. What's the leading coefficient? So in polynomial functions, if we were thinking of this as a polynomial function, we would label that as a sub 1. Of course, you're used to labeling that as m, all right, in the context of linear functions. They're the same. What is the leading coefficient here? Same as the slope. What? Yeah, 2/3, right? That's what you told me a minute ago. What's the constant coefficient here? You would label that as a sub 0 in the context of polynomial functions. So if you're thinking of this as a polynomial function, you would label that a sub 0. Of course, you're used to labeling that as, for linear functions, as b. What is that? -2, right, okay? That's the y-intercept. Now let's see, that linear function, does that conform to the other things that I told you about polynomial functions? So I said polynomial function can have at most how many x-intercepts? Same as what? The degree, right, okay? Well, how many x-intercepts does this linear function have? 1, right. It's only going to cross the x-axis once, correct? Because this is a straight line. So it's only going to cross the x-axis once. What's the degree here? 1, right, okay. And how many turning points can this have? The degree is 1, so how many turning points could that have? It's always 1 less than the degree. Well, what's 1 less than 1? So this can have at most 0 turning points. Do linear functions have any turning points? No, right, okay. They never switch from increasing to decreasing or vice versa, okay? Linear functions are either always increasing, right? Or they're always decreasing. Well, I guess they could always be flat too, right? But they're not going to switch from going up to going down or going down to going up. So not going to be any turning points there. Now, this also is a polynomial function, but you know that better as a quadratic function. There's the graph over there on the right-hand side again. Of course, the graph is just a parabola, so there's the graph. Let's see, as a polynomial function, what's the degree here? 2, right, okay? So quadratic functions have degree 2. What's the leading coefficient, which we would label as a sub 2, same as a with a subscript, same as the degree. What's the leading coefficient here? Don't say 5. It's -1/2, okay? The leading coefficient is -1/2. That's always the coefficient of the highest power term. So the highest power here is x squared, so its coefficient is -1/2. What's the constant coefficient, which we label, if we're thinking of this as a polynomial function, we would call that a sub 0. You usually think of that as being c when you're thinking of this as a quadratic function. What is that, though? 5, right, okay. Of course, that's the same as the y-intercept, right, which you can see up there. So according to those facts that I gave you about polynomial functions, what's the most number of x-intercepts you can have? Most number? 2, right, okay? So whenever the degree is 2, whenever you're dealing with a quadratic function, the most number of x-intercepts you can have is 2. We already know that, right? Okay, because the graph is a parabola, the most number of times it can cross the x-axis is twice, correct? And how many turning points can you have? 1, right, okay? That's the vertex, okay? For a parabola, the turning point is the vertex. Of course, parabolas are only going to have one turning point, right? Only one vertex, right? But that conforms to our knowledge of polynomial functions. All right, now let's try one a little bit harder. So this is a higher degree polynomial function. All right, so what's the degree here? 3, right, okay. So degree is 3. What's the leading coefficient? Which we would label as a sub 3. Helps to rewrite this a little bit. That minus x cubed over 3, you can write that as minus 1/3 times x cubed. That makes it a little bit more obvious. What's the leading coefficient there? Negative 1/3, minus 1/3, okay? And what's the constant coefficient? 2, right, okay? Because you have this constant 2 added at the end. Usually, by the way, when you're writing polynomials, you'll write the highest degree first, but you don't have to write it first, okay? So you might see this one written as minus 1/3 x cubed plus 4x and then plus 2, okay? So when we graph this, what are we going to see? You're going to see a smooth, unbroken curve, all right? So that's guaranteed, okay? Smooth, unbroken curve. And at most, how many times will it cross the x-axis? 3. It can have at most 3 x-intercepts. But it may not have any x-intercepts, all right? That's just the maximum number of x-intercepts it can have is 3. And how many times can it change direction? So how many times can it switch from increasing to decreasing and vice versa? 2, right. So that means you can have at most 2 of those turning points. Those peak points are the valley points. At most 2, okay? But maybe 0, all right? It's just at most 2. Actually, I have a graph of this one, so let's look at it. I think it's down here somewhere. Yeah, okay. So we do get, as promised there, this nice, smooth, unbroken curve, right? Okay, and indeed, it crosses the x-axis 3 times. So it has 3 x-intercepts, all right, and 2 turning points. There are the 2 turning points. A turning point like this, where it reaches a valley, that's going to be called a local minimum. So it looks like the coordinates for the local minimum here are -2 and -3, but I'm kind of guessing at that. I'm not sure if that's correct. And a peak turning point like this one, that's going to be called a local maximum. Looks like the coordinates for this local maximum are 2 and 7. But I just was eyeballing that, so I'm not certain of that. All right. So local minimum here, local maximum there at that turning point. Switching from decreasing to increasing to decreasing again. But again, notice, see a nice, smooth, unbroken curve. So you always get, again, when you're graphing polynomials, you're always going to get curves kind of like this one. They may have lots of wiggles in them, lots of places where it switches from increasing to decreasing, but always nice and smooth like this. That makes polynomials really friendly for using in lots of applications because they have nice properties, okay? The graphs are nice, and we can understand lots about the polynomial function just from looking at the formula, which is what we've been doing right here. So what's the degree of this one? 4, right, okay? So that's degree 4. So if you graph that, it may cross the x-axis how many times? 4, right, okay. So it may cross the x-axis 4 times, and it may switch direction from increasing to decreasing or vice versa. How many times? What'd y'all say? 3, right, okay. It may switch direction 3 times. It may have 3 turning points, 3 places where it changes direction, okay. Some of those may be those peak turning points. Those are called local maxima. Some of them may be those valley turning points. Those are called local minima. That's the technical term for those different types of turning points. What's the leading coefficient here? So you would label that as a sub 4. What is it here for this formula? Yeah, what's a sub 4? What's our leading coefficient? What? 1, yeah, okay. All right. I need y'all to answer back to me because I can't tell if you're thinking or if you're sleeping, all right? So I need for y'all to respond, okay? I know you know the answer to that, all right, but you're just sitting there like lumps, all right? Say something, okay? All right? That helps me know what we're doing here, okay? Otherwise, I'm going to call you, all right? And what's the constant coefficient, which you would label as a sub 0? Kevin? No. Constant means cannot be multiplied by a variable, okay? Because variables change, all right? So, so that won't be constant. 0, right. Why do you know it's 0? Yeah. Well, there is no constant there, right? Okay, there is no constant. So you can manufacture the constant, okay? You can actually manufacture the constant by just writing a 0, all right? So we could write this as x to the 4th power minus 3x cubed plus 2x plus 0, just to create a constant coefficient there. So the a sub 0 is indeed 0. What is a sub 2? So that's one of those middle coefficients. That's not the leading coefficient. It's not the constant coefficient. It's one of the middle coefficients. You have lots of middle coefficients here. What is this one? The way to look for that is, remember, this subscript is going to correspond to the power of x. So you're looking at this formula for a term that has x squared in it. Do you see that? No. So that means this coefficient also is 0. All right? That coefficient also is 0. You can create that term. You can create that term by the same way we created the constant, by just writing 0 times x squared. Okay? But that's not really a part of the formula. So that's 0. What's a sub 1, however? 2, right, okay, because the power of x there, that's 1, is this term, correct? So its coefficient is 2. So we already know something a little bit about the graph of this one. Here's what the graph of it actually looks like. So you get a smooth, unbroken curve there, right, just as promised. And let's see, does it have the right number of x-intercepts? There's 1, 2, 3, 4, right, okay, so it does have 4 x-intercepts. That's the maximum number, and we said it could have at most 3 turning points. Indeed, that's how many it's got, right? It ends up with exactly 3 turning points. Here, here, and here are turning points. This is called a local minimum. That's called a local minimum, and this is called a local maximum, all right? Peak turning point is local maximum. These valley turning points are local minimums. Actually, the plural for minimums is minima. So these are local minima, and then you have one local maximum. What?
So if we wanted to like put the maximum and min in like value terms, we could just put max and min.
Yeah, you can abbreviate it, right? Okay. Be careful though that you use the term local, because there actually is no maximum for this function, right? Because this function goes up to infinity on this side and also goes up to infinity on the left, okay? So there is no actual maximum there, right? Okay. This is just referred to as a local maximum for that reason. There is a minimum though, and the minimum is right here. The function doesn't get below this point, right? Okay, so that's both a local minimum and just a plain minimum, right? Okay, all right, so there's a little terminology about polynomial functions. We're going to look at a few more examples of them, okay? These are really the key facts, though, that we're going to learn about polynomial functions, all right? Polynomial functions, though, play, again, a key role for us in applications, and particularly in calculus, okay, because they have these nice properties that are easy for us to understand, all right? Another nice thing about polynomial functions is the formulas, although they might seem complicated, actually the formulas are quite straightforward, all right? Because the formulas don't have complicated arithmetic in them. Notice you just have powers, that's multiplication, and you have addition and subtraction. So the formulas, although they might have lots of terms in them, they're not complicated in terms of the arithmetic operations that are in the formulas. So that also makes polynomials very useful in practice. Okay. All right, now I have another sheet for you. We're going to try to start this one. This is an important skill that you do not get enough chance, or any chance maybe, to practice in the homework, okay? But on test number 3, you will have to be able to do this by hand, okay? So, because I want you to be able to graph straight lines by hand. You've already practiced that, of course. That's easy. But I also want you to be able to graph quadratic functions by hand, all right? Because those are simple enough that you can graph them by hand. Now, polynomials in general, those can be complicated graphs, right? So we really usually need technology to help us graph polynomials. But quadratics are simple enough that we don't need technology. Yeah, turn that one into me just so that I can record that, okay, that you worked on that one. I'll hand it back to you next time because I'd like you to have that with you when you're preparing for the third test, all right? So y'all got this activity? All right, now we won't get through all of this today, but let's see if we can get through parts. Well, actually, I'd like to try to get to C. Let's see how fast we can work here. All right, so this is just a parabola, right? Very simple formula, 3x squared minus 12x plus 6, right? Okay, so if you're thinking of that as a polynomial function, that's a degree 2 polynomial function, okay? All right, and we want to draw its graph, but we know the graph's going to come out as a parabola, right? So all we have to do is write down some of the key properties of the parabola, and that will allow us to draw its graph, right? So what key properties would that be? Well, what's its y-intercept? You know, if you got the y-intercept, that's an important piece of information in drawing the graph. Obviously the vertex, right? If you know where the vertex is, that will really help you draw the graph, okay? So we need that. And then also the x-intercepts, right? Okay? If we know where the x-intercepts are, then we can plot those on the x-axis, right? And then that also will help us construct the graph. Of course, you may not have any x-intercepts, right? So if we don't have x-intercepts, that makes things worse. But hopefully it'll have some x-intercepts. It definitely has a vertex, right? Because every parabola has a vertex. Every parabola is going to have a y-intercept. So see if you can get the where the y-intercept is. That's trivial. Where the vertex is located at least, and then get started at least on finding the x-intercepts. Okay? Yeah, I'm going to collect 6. Yeah, we didn't do the roll, so I will pass out the roll at the same time. So while you are finishing, are working on the key properties of that, right? Okay. I'll pass the roll around. Okay. All right. So, but when you leave, turn in 6. You can set it somewhere here. Set it on the white table. I can record that as an easy homework grade, so that will slightly boost your homework score. See how fast you can. You don't remember the vertex formula there? I've got it somewhere. Let me see if I find the notes there. There it is. There's the start of the vertex formula, right? Once you find the x-coordinate, then you can plug that x-coordinate into the formula to get the y-coordinate, right? Okay. So the key thing is being able to find the x-coordinate of the vertex. I think this vertex works out easily. I think it's going to be whole numbers, not fractions. But the x-intercepts, I think, do not come out to be whole numbers. Did you find the vertex? Oh, yeah, that's good. Okay. So that's easy. I don't think that's the right y-coordinate there. Did you plug the... No. You take the 2 and plug it back in, right? Okay. All right, so you got... Yeah. All right, so you're simplifying that. So there's the first coordinate. What's the second coordinate? Right, because the vertex is a point, right? So how do you find the second coordinate?
Oh, do you plug it in?
Yeah, you plug it in, right? Yeah, you plug it into your formula. Right. All right, did you find the... That's going to give you the x-intercepts. What about the vertex? Let's find the vertex first and the y-intercept. What's the y-intercept? That's pretty easy. 6, right? So just write that there. That's where it's going to cross the y-axis is 6. Now, do you remember how to find the vertex? That's the vertex formula. You start with minus b over 2a. That's the x-coordinate. Yeah, so what does that work out to be?
So this is 6, negative 2.
Be careful because this is negative 12, right? So, and it's minus b, so you have minus a minus. All right, so that's, yeah. All right, so that's the first coordinate of the vertex, but you got to get the second coordinate as well because vertex is a point. So it has 2 coordinates, right? There's the x-coordinate, so you got to get the second coordinate as well. I don't think that's 18, so you want to off in your arithmetic somewhere. So 12 minus 24 plus 6 is what?
12 minus 24 is negative 12.
Plus 6 is
Negative 6.
negative 6, right? So you wrote 18, right? Did you get the... All right, so yeah, you're off here in your arithmetic. When you plug that back in, check your arithmetic there.
6, yeah.
2 minus 6. Great, yeah, that's the vertex.
Yeah.
All right.
Okay.
All right, so now we know where the vertex is. We know, and now we just, if we can find the x-intercepts, then we'll be in great shape. We can plot those points, I think, and make a graph out of that. Okay. All right, so that's where the x-intercepts are going to be. But before you even get to the x-intercepts, those are kind of the harder thing. What's the y-intercept going to be? 6. That's right. It's 6. It's always the constant coefficient. Yeah. Okay. Right. So 6. Is it minus 2?
Wait, when you plug in the formula, is this a negative 2 as well?
No, it's minus b over 2a, but it's minus b, but b is negative 12, right?
Okay. So it's just
2, right. Now, how do you find, that's the x coordinate of the vertex. How do you find the y coordinate of the vertex? Because the vertex is a point, so it has 2 coordinates. So, where is the, how do you find the second coordinate?
You plug it in.
You plug it in, right? So take the 2 and plug it into the formula, right? Okay. Did everyone sign? I think so. Everyone signed? Yeah, okay, yeah. All right.